Dynamic General Equilibrium Modeling by Burkhard Heer and Alfred Mausner, Chapter 10.1, The Overlapping Generations Model and Income Uncertainty. Hello and welcome to the presentation of this chapter from our book Dynamic General Equilibrium Modeling. Today I present the most important model for the consideration of income and wealth distribution in economic theory. So we want to study anything like what's the distributional effect of a tax policy, what is the distributional effect of aging, of the demographic transition, how does it affect income and the wealth distribution, how does a COVID crisis affect the distribution, are we having many more poorer peoples, or are we having a more higher concentration among the rich people? What are the consequences of all these shocks and policies, fiscal policies? Well, economic researchers like me, they use this prototype model of income and wealth distribution that I will explain to you in the following. A second point is that we will look at is how we compute this model, and this is also taken up in our book where we describe the details of this model and its computation. And then this might be important for someone who's starting to computer programming and coding. We will compare three computer languages, which are rather common right now. These are Python, Julia, and Gauss. And Python by now has overtaken MATLAB and others in terms of applications. It's becoming probably the most important numerical tool in economics and computational economics, far more important than R, for example. And its main advantage with respect to languages like MATLAB or also Gauss that we will consider is, of course, it's free. There's lots of material in the internet, and it's very successful also in other areas besides economics, other scientific disciplines. Now there's a second freeware that's very interesting to economists, which is Julia. And we will also look at the code of Julia and compare it to Python and also Gauss, which is kind of an old software from my generation, which we use a lot for econometrics. And we will find out that Julia and Gauss are far more faster with much higher computational speed than Python. So in our applications where programs sometimes need hours, days to compute an equilibrium, a transition, a distribution, well, we often choose Julia over Python in terms of speed. This will be one of our results, especially when our models suffer what we call from the curse of dimensionality. If we have a lot of individual state variables, for example, in our model, individual state variable will be the wealth of the individual, his productivity, his age, and also how much earnings he or she has accumulated with respect to pension entitlements. So this is a 4- or 5-dimensional state, and this suffers from the curse of dimensionality. It takes a long time to compute this stuff. We have a lot of nested loops to compute this, and in these loops, Python is particularly slow, while Julia and Gauss are much faster. And to already give you the idea how this compares to other languages that you might use, well, you can always use Fortran and C++, which are the really basic computer languages for this coding. But these are languages which are kind of difficult to program. So to set up a C++ program, it takes you much longer than set up a Python or Julia or Gauss program. So these high productivity languages, as we call them, Python, Julia, and Gauss, are more efficient when you have to code them. So, and you always, as a coder, you have to weigh advantages and disadvantages, a trade-off between cost and benefit. And of course, there's a cost if you have to take a long time to write your C++ or Fortran program. And the benefit, of course, is that it's faster in its computation. Well, a lot of you might know MATLAB, which was very popular in recent 2 decades. And with regard to MATLAB, which is kind of expensive, while Python and Julia are free, Gauss is all pretty much as expensive as MATLAB. Well, we find also that MATLAB is too slow in many aspects for our large-scale heterogeneous models. So we have not taken up this. I've analyzed this in my other book, Public Economics, and MATLAB programs, and I found them too slow in comparison to these languages here, in particular Julia. Okay, let me tell you something about the prototype model of income and wealth distribution, which we use for policy analysis and also for other analysis like shocks to the economy, like COVID or the financial crisis, and to find out how it affects the distribution of wealth, of income among the individual households in our economy. Now, the research questions, let me summarize them. What is the prototype overlapping generations model for the study of redistributive economic policies? How do we compute it? This will be basically value function iteration. And the trade-off in speed and accuracy, which algorithm computer language should we use? Python, Julia, or Gauss, or possibly others. Now, why do we use the overlapping generations model as our prototype model of income and wealth distribution? Well, its main advantage are the life cycle savings. So of course, people at age 20, 30, students like you, for example, and senior researchers like me, well, we have different levels of wealth simply because you're young and I'm old, and I've accumulated hopefully a little bit of wealth for my retirement. So the life cycle savings aspect is really important. That's why we study overlapping generations model, which allow us to model the generational, the cohort structure of an economy. Well, there's some substitutes for this in the literature. For example, when you think of the simple neoclassical growth model, the Ramsey model, well, we can also introduce 2 kinds of people, for example, in this kind of model that, for example, with a certain probability, that's usually the technique it's implied, workers retire and then do not earn income anymore. So that we have 2 types of workers, those who are workers and those who retire, and sooner or later they will die with a certain probability. This is often used as, well, as a substitute for the life cycle savings model, but it does not allow you to model the age structure in the economy. And this is really important because if you look at the age structure, you find that people at age 50, 52, or even 55, my age, well, they are more productive than people at age 20 or 25, almost by a factor of 2. Now, if you want to study, for example, the effects of the demographic transition on production in the economy, on income, on wealth and everything, of course you need to take into account that the labor force is composed of old or young people and how productive these people are. And you cannot capture this with this model where there's just 2 states, worker and pensioner. So it makes a lot of sense to use an overlapping generations model if you want to get the age structure and the productivity structure among the workers right, and want to say anything about redistribution between different cohorts and generations. The next important element in our analysis is uncertainty of lifetime. So some people die early, some people get sick, and others live very long. And because you are actually in danger of living a long life and hopefully fulfilling life, you accumulate a lot of savings. There's a big literature, for example, by Maria Cristiani Di Nardi, and she pointed out that medical expenditures in old age go up dramatically. So at the age of 60 or 70, it's about $1,000 in the United States annually. And 10 years later, you have to pay something like $10,000 on average for medical expenditures. So what you do as an rational individual with some foresight, you put aside a lot of savings for these times when you're old and you may have to pay uncertain medical expenditures. And of course, if you live long, you also have to somehow finance your old age. You get a pension, a public pension, but this may not be enough. So rather safe than sorry. You save a lot for old age because you do not really know when you're going to say goodbye to this world. Another uncertainty that's important in the modeling of the distribution of the income and wealth distribution are uncertain earnings. So perhaps you have a good strike and you earn a lot, and then something like the COVID-19 crisis strikes, or the Great Recession from 2007-8 strikes, and you lose your job, or you have to get a job with lower pay. And because of this, you build precautionary savings for these bad times. So the uncertainty of your income is also a basic explanatory element, reason why you save and therefore become perhaps richer as others. This will help us to explain the wealth distribution among the individuals. Now, I've already mentioned it. You have to somehow finance consumption, medical expenditures, and others in old age. And in modern economies like the United States or continental Europe or Great Britain, we have pay-as-you-go pensions. So the government takes money from the current workers, they have to pay contributions, and allocates it to retirees who have some entitlement to pensions. And most often the entitlement depends on their contributions. So in Germany, it's, for example, basically 1-to-1. In the United States, well, it's not proportional. So those who have little contribution, they do not get basically zero pension, but there's some redistribution within the pension system. Now, and when you know that you will get a pension in old age, you save less. So this is a basic explanation of savings and accumulation of wealth. We have to include pay-as-you-go pensions. And finally, the fifth element that's really important is endogenous labor supply. And I will tell you about this when we look at the distribution in the United States. So here we have some data in the left column for the United States, which is taken from Butria Rodriguez, Diaz Jimenez, Quattrini, and Victor Rios-Roll, and from Dirk Krüger, wages in the United States, well, they are characterized by a Gini coefficient of 0.375. Now, the Gini coefficient is a measure between 0 and 1, of course, and 1 meaning that we have complete concentration. Just one guy gets all the wages, all the earnings, or all the wealth. And 0 means that we have an equal distribution, and 1 has the same. Now, starting from the wage inequality as characterized by a Gini coefficient of 0.375, we have a Gini coefficient of earnings somewhere between 0.4 and 0.66. So it depends a little bit on the database, whether you use, for example, Consumer Survey Finance, CSF, or PSID data, and which period you use. So, for example, Butria Rodriguez finds something like 0.66 and Krüger finds something like 0.43 as the Gini coefficient of earnings. Now, to get from a wage Gini of 0.375 to an earnings Gini of something like 0.5, for example, well, you need inequality in the labor supply, because earnings are basically wages times labor, times the hours you work. And what we find in the data is that people with high wages, high productivity, work more hours. And therefore, we get more inequality in earnings than in wages, and that's the reason we need endogenous labor supply in order to replicate the earnings distribution starting from the unequal productivity distribution, unequal wage distribution. So somewhere you have to start. Somewhere there must be an origin of inequality in our model. You can start with unequal abilities at birth, so that people have, for example, different intelligence. You can start with different human capital distribution at the start of the working age, or you can start with the productivity distribution of the workers, and that's where we start with, where most models of distribution start with a distribution of the productivity among the workers, which translate into a wage distribution characterized here by a Gini coefficient of 0.375. Not only the earnings distribution here is endogenous in our model, but also the wealth distribution. And I've already introduced you to the different motives for savings. And in our model, we get a Gini coefficient of 0.66. So in our overlapping generations model, well, the Gini coefficient of wealth is almost twice as high as the Gini coefficient in wages and much higher than the Gini coefficient in earnings. And that's a particular feature characteristic of the overlapping generations model, which was shown by Mark Hoggett, that it can generate a lot of wealth distribution and wealth inequality and gets close to the empirical value of 0.80. Not perfectly close, but very close. So to get from 0.66 to 0.80, well, you probably have to add two basic things. One are bequest. So rich people often give a lot of money to their progeny, to their children, who become rich as well. And the second one is entrepreneurship, self-employment. So in our model, we have no Bill Gates or Elon Musk. And these are the people, of course, which are important for the top 1% of the wealth distribution. So let me show you how the Lorenz curve of the United States and the model that we will compute in a couple of minutes. The red line is our model, and you can see it's very close to the blue line, the equal distribution. So we can read this Lorenz curve as follows. So the first 10% here, they basically earn 0% of earnings. The lowest, the 50%, the lower half of the earnings earner, the poor earnings earner, have about 18% of total earnings. And if you look at the top 10% here, which are located here, so these top 10%, well, they earn, in our model, they earn something like 38% of total earnings, and empirically it's about 42% here, which is their share in total earnings. Now our model generates an endogenous wealth distribution that is characterized here, displayed by the red line. And as you can see, we are modeling the empirical distribution of wealth in the United States closely for the low wealth people, for the poor people, wealth poor people. So in our model, the 30%, the lowest 30%, the lowest 3 deciles of the wealth distribution own basically no wealth. They're credit constrained, they're at a zero credit constraint. And then the lower half of the wealth distribution just owns something like 7 or 8% of total wealth, both in the model and in the United States. And then our two Lorenz curves, they start to diverge. In particular here, the top 1%, which empirically owns about almost 30% of total wealth, and in our model it's only about, 4 or 5%. That's where our model fails. So our model does not have Bill Gates or Elon Musk, and that's why we fall short here in this area. Now we will compute this model with the help of value function iteration, which is basically the only way you can compute models with heterogeneity and stochastic. There are basically no other method how you can compute it. But in this value function iteration, there are a couple of choice variables. So how we do the optimization step where we maximize the right-hand side of the Bellman equation. And one difference might be how we interpolate next period value function, either linear or cubic. That's what we look at. The number of grid points that we used, the accuracy that we would like to get. And what I would like to point out to you here in this introduction is the runtime. So we compared the runtime of Julia, Gauss, and Python. We basically programmed exactly the same program. So if you go through it line by line, there's basically no difference. So we have the same number of operational steps of computations and the number of computer lines. And as you can see, let's take, for example, the case where we have cubic interpolation with 300 grid points on the Ethernet grid, on the Wealth grid. Well, in Julia and Gauss, it takes about 45 minutes, 50 minutes to compute it on our machine here. And Python, we need 48 hours. So it's larger by a factor of at least 50 in this particular case. And in other cases that we study, we find that it's also, well, much slower than Julia or Gauss by a factor of 10 to 50. So Python is really slow in the computation. And in our large-scale OLG models, this might be a constraint that's effective, and that's why, for example, I choose either Julia or Gauss to compute my models. Other researchers even take one step further and go to Fortran or C++. But Python is slow. Okay, now I've got some download information for you. You can download all the Python, Julia, and Gauss code together with the slides from our homepage. And we also have a Python program tutorial, a Jupyter script available for you that goes through the Python code line by line, block by block. And the Python code is really similar to the one in Julia and Gauss. So even if you prefer to do programming Julia or Gauss, or even may resort to MATLAB or R, you can use this Python script because the syntax may be a little different between the different commands, but the whole program basically, it's almost one-to-one. You can copy it one-to-one into your editor and just have to change the syntax. So let me take a look at these pages. So the first page that I would like to point out to you is our homepage for the book, Dynamic General Equilibrium Modeling, Computational Methods and Application, which you can just Google, or you can just copy the address here from the menu bar. And if you scroll down the page, you find Gauss, MATLAB, Python, Fortran routines, Julia, and more. So you find all the code on this page. If not, just send me an email and I will be happy to provide it to you. We also have a new page here where you can look at particular scripts. These are Jupyter tutorials here, Jupyter scripts for chapter 7, 9, and 10. I have set out a couple of Python codes descriptions. So let's take a look here at chapter 10, computation of the 70-period OLG model with idiosyncratic uncertainty using value function iteration. This will get you here. And on this page, well, we have collected the Python code and explained it in detail. So first, we describe the model and its calibration. And next, we go through the model step by step. So we look at particularly blocks of the model, let them run in Python, show you the output, and discuss the individual line, what we are doing in each of these blocks. So it's a really detailed tutorial of what we are doing here. So sometimes we, for example, show output here, and we'll describe how the computation in the model takes place. So for example, here in equation 31 through 33, we explain to you the computation of the measures of the different cohorts in the model. And this is done in the next block here, for example, in the block 4. And the distribution of measures in our model from the 21-year-old to the 90-year-old here is displayed in this picture. So you can use this Python script to understand the code in detail, and it's also applicable to the Gauss code, to the MATLAB code, or to this Julia code. They're very, very similar. In the following, we will discuss and describe the model, the prototype, the benchmark model for the study of distribution policies. We start with the demography, and then we describe the different sectors in turn, the household sector, the production sector, and the government sector, and just give you a hint what's the stationary equilibrium, so where survival probabilities are constant, the shares of the population cohorts are constant, and we can study something like a steady state. So let me get into the slides and describe to you the model, starting with the demography. Now, every year a new generation of equal measure is born. They start real life age at 21, so this corresponds to our index s equal to 1 in the model. Households live 70 years at a maximum, so they become 90, and afterwards they die for sure. But not all households, not all persons will reach age 90. There's a stochastic survival probability, and it's denoted by phi s. So let me show you the survival probabilities in our model here. They are taken from the year 2015 from the United Nations. And as you can see, the 21-year-old, which is our index s equal to 1 in the model, our age index, well, they basically survive with a probability of 100%, and the probability declines monotonically and even a little faster in old age, so that the 89-year-old become 90 with a probability of 90%, 10% die, and the 90-year-old ones, they die with certainty. The first 45 years of their life, so corresponding to age 21 through 65, they are working and supply labor supply LST, so at HS in period T, so that leisure is 1 minus LS. And after retirement, leisure goes up to 100%, and vice versa, labor supply drops to 0. And the maximum number of retirement periods amounts to 25 periods. NTS denotes the number of S-year-old agents in period T, and NT is total population. So we have to define two different growth rates. One is the growth rate of population, GNT, which describes the population growth rate of total population, and the cohort growth rate, NT, lowercase nt, which describes just the growth rate of the 1-year-old in our model. And during the transition in a non-stationary equilibrium, well, these two need not be equal. So right now, the 20-year-old, 1-year-old in the United States, their growth rate, their population growth rate is different than the growth rate of total population. But in stationary equilibrium that we study in this section here, in this video, Gn and n will be equal to each other, and the phi s will be constant, the values calibrated from the year 2015. Our population growth rate will be 0.754%, just like in the first decades of this century in the United States. Households, the first sector here, households, they maximize intertemporal utility. And utility is a function of consumption. Instantaneous utility U is a function of consumption C and leisure 1 minus L. It's discounted by a factor beta, which we will set to 1.011 according to estimates by Hurd in Econometrica. And also, of course, the survival probability enters our effective discount rate. So our effective discount rate is beta times phi S for the S-year-old. And we also have a term V of G, which is the utility from government consumption. It's entered additively, so it does not affect our optimal labor supply and our consumption C and L. When we look at the first order conditions, these terms drop out. So without loss of generality, we may even set it to 0 here. Instantaneous utility is Cobb-Douglas with weights gamma and 1 minus gamma. So the weight of consumption in utility is gamma. And we calibrate gamma so that labor supply is equal to 0.3 in our stationary equilibrium, and that therefore we set gamma equal to 0.33. Eta is our inverse of the intertemporal elasticity of substitution, and empirical values vary a little bit. So there's evidence it's close to 1, but the interval 1 to 4 is fine for the parameter eta, and we set it to a value 2, which is often used in the literature. Our net labor income, Y, is wage income times taxes, times what's left of taxes. So we have 2 taxes here. Tau L is the wage tax and tau P is the pension contribution rate. And the wage rate W per efficiency unit times the labor supply times the productivity of the worker is our labor income. Now we have a couple of components here. AT, which is aggregate productivity, which grows at an exogenous rate GA, and it's set to the growth rate in the economy. So in the United States over the last 20, 30, 40 years, 2% is a reasonable value for the economic growth rate in the United States. And our individual productivity, epsilon, depends on 3 variables. S for HS, idiosyncratic productivity, theta, which is stochastic, and E, which is a permanent productivity. So that's often applied in OLG research, in dynamic general equilibrium research, that these 3 components can be distinguished, which affect individual's income. Individual income is uncertain, so there's a stochastic component which is captured by the variable theta. There are differences between people, for example, with a college education and a high school education. This is captured by the variable E, and there are differences in age productivity, which is captured here by the H index S. So to give you an idea about the age component, well, Hansen estimates the following age productivity profile. It's sum-shaped. Well, we have 2 kinks here. Some authors smooth this function by using a polynomial, fitted by a polynomial of order 2 or 3 or 3. We will just use the original data by Hansen here. And as you can see, maximum productivity, age productivity is 51%, which means that on average, 51-year-old earn about twice as high. The hourly wage of the 51-year-old is twice as high as the wage of the 21-year-old. So here you can, of course, immediately see that it makes a difference if we have an old labor force, which is composed mainly of these people with high productivity, or if we have a young labor force, which is mainly composed of people at age 20 to 30. And of the older labor force, according to the estimates of Hansen, is more productive. So this gives some reassurance to me, for example. I'm 55, so I'm here. It might not be true for all professions. So, for example, researchers or mathematicians, for example, their productivity peaks prior to age 30. And for economists, well, it peaks a little later, but I'm not sure I'm more productive now than I used to be 20 years ago. But on average, in the economy, in the United States economy, we observe this wage age profile. So we have three components which we specify multiplicatively. So our epsilon, our individual productivity here, is theta, our idiosyncratic component, E, our permanent component reflecting high school college pay differences, and our H component bar YS. We estimate the productivity of the high school and college educated E with the help of data from the skill premium. The skill premium of college educated students, graduates, is 150% vis-a-vis the high school students. So if you add 150% of 0.57 to 0.57, you get to 1.43. And we have normalized these two values to be equal to 1. Similarly, bar y, the average is normalized to 1, and so is theta. Now there's a big literature starting in the, or probably prior to the 70s, but that's what I'm aware of. And most recent literature by Gyvänen, for example, they look at the stochastic component and on income, its stochastic behavior, especially stochastic behavior of earnings, and they estimate this stochastic productivity theta to follow an autoregressive process. So a logarithm of theta is autoregressive with parameters rho and a disturbance theta xi, which is normally distributed, and we take estimates from Hoggett to estimate the stochastic productivity. Well, if you assume that households start at age 21 with a log normal distribution of theta, well, if you impose this autoregressive process, then wage distribution will continue to be log normal. That's a useful property. But recent evidence by Zeiss, by Gyvänen, they've pointed out that it's not a perfect fit. So especially when we look at the long, big, fat tail of the very rich people in this distribution here, the really high potential wage earners, it's bigger, it's fatter than the normal or log normal distribution. So this is an approximation. So if you want to study distribution effects and concentrate on the very rich people, the Bill Gates, the Elon Musk, then you have to use a different specification to capture the very rich people and their wage or earnings income. Now, the retirees just receive lump sum pensions, and in the paper we also study the case that we have earnings dependent or contributions dependent pensions. Now this introduces a new state variable, continuous state variable, the accumulated earnings. And this, therefore, our computation is even more under the curse of dimensionality. And we discuss it separately in the book because it's such a demanding job to have a second continuous state variable. So we have one state variable, individual state variable, which will be wealth, and we will have, in the special case, also have accumulated earnings as a state variable, continuous state variable. All the other state variables like productivities, they will only be a discrete number, a small number, but with wealth and accumulated earnings, we have many grid points that we have to choose to approximate the distribution here. Well, this becomes really cumbersome and slow to compute these kinds of equilibrium, and we will study it. For this case, we will study it separately. The budget constraint of the household. So the household holds two kinds of asset, capital K and government bonds B. Capital K has the return R. If I lend capital to the firm, they give me return R. Capital depreciates at rate tau, and I have to pay taxes on my returns at the percentage points tau K. And as you can see from this specification, depreciation is tax deductible, which is good approximation for the United States. The government bonds, they earn interest rates RB, and we don't have to pay taxes on them. Now, of course, when the individual decides how much he carries over and how much capital and government bonds it will accumulate for next period, say for next period, well, it invests in the asset with higher returns. Now, therefore, in equilibrium, we can only have equal returns, net after-tax returns to these two assets. So 1 minus tau K times R minus delta must be equal to RB in equilibrium. Otherwise, the individuals would shift all their assets into the asset with a higher return, and this would, of course, in the capital markets, in the physical capital market for K and the government bond markets B, result in an equalization of the two returns. So we have, of course, an arbitrage, with arbitrage would imply equal returns. And that's what we're going to impose. So what we will study is we can study the behavior of assets, of wealth in our economy, which is the sum of capital and government bonds. And it will get the return RB, or equal to the return 1 minus tau K times R minus delta. And we do not need to distinguish between K and B in the household. We just reduce it to one state variable, assets A. Now, we do not know how the individual assets are composed. So what's the share of K and what's the share of B for each individual with productivity theta, E, and HS, and wealth A. We cannot determine this. We will just assume, without loss of generality, that each individual holds the assets K and B in the same proportion as in the aggregate. So the individual ratio of capital to individual wealth A is simply the aggregate equal to the aggregate, so the ratio of the aggregate capital stock to aggregate savings. Okay, this is not a problem in this standard neoclassical model where you have a representative household. And of course, a representative household, since we only focus on one household of measure 1, must hold the assets K and B in the same proportion as in the aggregate economy. Now, besides labor income, after-tax labor income, Y and asset returns RB and 1 minus tau K times R minus delta, the household receives transfers from the government, which will be very small percentage of GDP, so just 1 or 2% in our model, and spends it on consumption and savings. And consumption is taxed at rate tau C. So that's the budget constraint of the household equation 4. And we study the optimization problem of the household with the help of recursive formulation. And we use the value function here, and our value function is defined for the S-year-old is defined as the maximum of utility, instantaneous utility, plus discounted next period value. The value function is a function of the variables theta, E, A, and HS, and we summarize it in this individual state variable ZS. In next period, the value function is a function of ZS plus 1. The household maximizes the right-hand side of this equation 5, which we call the Bellman equation, with respect to consumption, labor, and next period wealth. It discounts next period value function by beta times phi s, the survival probability. And here we have the transition probability that for present idiosyncratic productivity theta, next period productivity is equal to theta prime. And of course, theta prime enters our state variable zs plus 1 in the next period at hs plus 1. And depending on theta prime, our value function will be higher and lower depending on the value of theta prime. We also impose a budget constraint so that a household cannot indebt itself, so A is larger or equal 0. Now the rest is fairly standard in this model. So we have a production sector where firms are subject to perfect competition, both in goods and factor markets. The production function is Cobb-Douglas as presented by equation 6. The firm maximizes profits, which is production minus wage cost minus interest rates cost. And factors are rewarded by the marginal product. So wage is equal to the marginal product of labor and effective labor, ATLT, and the interest rate R is equal to the marginal product of capital K. The government sector, we distinguish a fiscal authority and a social security authority. So total taxes are given by labor income taxes, tau L times ATL T WT, by capital income taxes, tau K times RT minus delta times K. Notice that we have K here, not aggregate savings omega, because there are no taxes on the interest on government bonds RB. And consumption taxes tau C times uppercase CT. So with uppercase variables, we denote aggregate variables like consumption or government consumption. And with lowercase variables, we denote individual variables. Now the government has expenditures, aggregate transfers, aggregate government consumption G, and interest payments RB times aggregate government debt B. And this is financed by taxes, by accidental bequest, which I will get to in a second, and by debt. So the BT plus 1 minus BT is the increase in debt of our government. So where do accidental bequests come from? Well, some of the households, they simply die. So only phi s of the households is the share of the households survive from HS to S plus 1, and the other one dies. And so far, we have not introduced something like a parent-child link, that parents who decease bequest their wealth to their children. Now, we introduce a government here that has a function to collect all these accidental bequests and pass it on to the household, and it will pass it on lump sum. So this is a shortcut for handling bequest in our model. If you want to introduce bequest, well, then you introduce another state variable, which is of course the wealth of the parents. So if I'm, for example, rich, if I have rich parents, I know I will get a high bequest, for example, in the future. So today I save less. It affects my savings. And vice versa, if I have poor parents, well, I have to save a lot myself for old age because I'm not happy or fortunate to inherit a large estate or a large amount of inheritance from my parents. So there we have an additional state variables, and each additional state variables, in particular if it's a continuous state variables where we have to use a lot of grid points to approximate the distribution, well, makes our computation very cumbersome. So let me give you the expression for the accidental bequests here, which is given here in this equation. So those who die, which have chair 1 minus phi s, they leave behind assets a prime and then times 1 plus the net interest rate. Why do we use next? So next period's bequest are equal to next period's wealth times 1 plus the interest rate. Where does the interest rate come from? Now that's the timing in the model. So people accumulate, they work, they get the interest rate, and then at the very last second of the period they consume, and then they either survive or they die. So next period, if they die, we have assets A prime at the beginning of the next period. And then in the next period, production takes place over the whole period, working takes place over the whole period, and these assets A prime that are left to future, which are inherited by the government, to say so, of course they earn interest, and then at the end of the period they are paid out to the households as transfers, and they can consume it or save for next period. So that's why these assets still accumulate interest over the period, and it's proven in our book that this specification here is the correct one. So if you insert all these equations into the budget constraint of the household, what you derive is that in equilibrium, let me show you the equilibrium condition, that the goods market equilibrium holds. That total production is equal to consumption plus government consumption plus investment. Only this specification that the bequests are equal to assets plus interest implies that our goods market equilibrium equation 12 holds. The second government authority here is the Social Security Authority, and they just run a balanced budget, so the total pensions they pay out is equal to total pension contributions, and total pension contributions are simply Social Security rate tau p times total wage income, which is equal to AT LT WT. To aggregate productivity AT, aggregate efficient labor L, and the wage rate W. Now, our equilibrium conditions are that total savings, total wealth, which we call omega, is equal to total capital plus government bonds. The two after-tax return must be equal. And we have aggregate consistency conditions so that the sum of the individual variables is equal to the aggregate variables. We have the goods market equilibrium, and we now want to describe a stationary equilibrium so that we can compute an equilibrium where survival probabilities are constant, population growth rate is constant, and the distribution across the cohorts is constant. Our population is still growing, but we divide everything by the size of the population, all aggregate variables, and then, so that we have consider a stationary distribution of the cohort shares. Now we get to stationary individual variables by dividing through total productivity AT, and we get to stationary aggregate variables by dividing through total productivity AT times total population NT. Now this holds for the individual variables C, Y, K, and B, and for the aggregate variables mentioned here in this list. We do not need to divide individual labor hours by AT, because this variable is already stationary, and aggregate efficient labor L we only divided by the number of people NT. And we can also reformulate our model in stationary variables so that we can use it for our analysis. So in stationary variables, for example, the individual budget constraint is given by equation 13. So notice that here 1 plus GR, 1 plus the growth rate enters when we divide by 80, the individual budget constraint. And we can also formulate our net labor income here in terms of stationary variables and our Bellman equation here. Okay, and the computation in our model, the main problem here is to compute the solution to the Bellman equation and to compute the distribution. Now the distribution, we have a couple of variables here. Let me show you all the variables that we look at. We have the variables SH, the idiosyncratic productivity, theta. We have the permanent productivity, high school, college graduates, E. We have individual values, A. Now we study a distribution here. We normalize total population to 1 and the shares of each cohort will be constant. And of course, here we have variables which are discrete. So we have age going from 1 to 70. We will use 5 idiosyncratic productivity, theta. We have 2 permanent productivities. And we have a continuous state variables, which is wealth. Now a computer program cannot compute the continuous variable at each point because there are infinite points on let's say an interval from a equal to 0 up to 20. 20 will be our maximum. Nobody will hold more than 20 in our model. So what we do is we compute this distribution at grid points. For example, we will choose 500 grid points for our valve A. And as you can see, the individual state variables are really these variables which enter a lot of computational time and capacity. If we had another variable, for example, accumulated earnings, they would enter a lot of grid points again to approximate the continuous state variable. And if we had something, for example, like the wealth of the parents, we would have another state variable where we, for example, might need another 100 grid points or something like this. And of course, to compute all these grid points, 70 ages, 5 idiosyncratic productivities, 2 permanent productivities, and let's say 500 points A here. Well, this amounts to a lot of computations, because for each of these different discrete points, we have to compute the optimal policy function, consumption, labor, next period assets and savings. And this means we have to solve this stationary Bellman equation here for all these grid points. And of course, this will imply a high computational time. So in our case, with Julia or Gauss, it will take something like an hour. And with Python, it will take something like 50 hours to compute this equilibrium. And we need to be really careful how we choose the number of grid points, which the grids, and the number of continuous state variables. So let me explain to you, for example, the equations 19 and 20, which are simply the aggregate consistency conditions. So the aggregate labor supply here, L, is equal to the individual productivity epsilon, depending on age, idiosyncratic and permanent productivity, and its labor supply, which of course also depends on these 5 state variables here, times the measure of these agents. And we sum up over all the measures, all the households at different times to get aggregate labor, and similarly, for example, for aggregate savings. Now, the tricky part, of course, will be to derive this policy function here, for example, for labor, and the distribution F. Before I will describe it in the next step, let me just tell you how I calibrated the model. And I used fairly standard values, mostly taken values, calibration values from Trabant and Ulich. So the production elasticity of capital equal to 35%, depreciation rate in the United States of 8.3%, growth of output of 2%, and intertemporal elasticity of substitution of 1/2. Gamma equal to 0.33, so that our labor supply is approximately 30% in equilibrium, and a discount factor beta taken from from the estimates by herd. Population growth rate of 0.754%. So these calibration values I already mentioned in the description of the model. We have 3 tax rates here. The sum of wage tax and pension contribution rate equal to 28% in the US. Capital is taxed at 36%, so tax rate on capital income is higher than the tax rate on labor income. That's different in other countries. For example, it's just the opposite in Germany. Tax on consumption is 5%, and we have government share here, 18% government consumption in GDP. And debt output ratio, we take the value that's used by Trabant and Uri, 63%. Looking at the Corona crisis, we've seen that debt levels went up in the United States, and we have debt output ratios in excess of 100% now. You are invited to compute all our results, recompute them with higher debt output ratio, and see how higher debt affects the distribution of income and wealth in our economy. The replacement rate is chosen to be 35%, so the replacement rate is defined as pensions relative to average wages, gross wages, prior to taxation. And the permanent productivity types are chosen so that we have a skill premium of 150% and an average permanent productivity of 1. Now the different part here is the calibration of the stochastic component. So we discretized theta with 5 grid points and choose a log normal distribution of those who start working, the 21-year-old. And we take this log normal distribution with variance 0.38, this calibration from Haggett 1996. And we use an equally spaced grid on logarithm theta. So we use the values for logarithm of theta equal to minus 0.756, minus 3.7 and 0 and so on. And you can notice that the distance between the grid points is equal. And we compute the distribution at age 21 by assuming that there's a logarithmic function, and we just compute the error between minus infinity, for example, to the midpoint between these two here to minus 0.5 something, and then the measure of those who start with productivity logarithm theta equal to minus 0.378. We just take the neighbor 2 midpoints here, so minus 0.5 till minus 0.18, and just use the area under the normal distribution to compute the share of people with productivity minus 0.378, and so on and so on. So this gives us the shares, which you can see here, which are equal to nu theta. So the share of the one with the lowest productivity is 17%, and those with the medium average productivity is equal to 0.2. This is equal to 24%. Now the question is how we choose this grid here, the distance between those, the equal distance, and we have chosen it so that the Gini coefficient is equal to 0.37. So therefore we choose an equally spaced grid over minus variance, minus the standard deviation sigma y1 to plus 1 sigma y1, and if we had chosen a wider grid here, this would have implied a larger Gini coefficient, which would not be in accordance with the data. So that's how we start to model the distribution of productivities at the first age, at real lifetime age 21. And then we look at the dynamics of these individual productivities, and therefore we use the estimates by Haggard that theta follows an autoregressive process which does not depend on age, but is described by this AR1 process, and theta prime, the logarithm, is rho, the autoregressive parameter rho, times logarithm theta in the previous period plus xi, the normally distributed disturbance, and Haggard estimated rho equal to 0.96 and the variance of this error term here equal to 0.045. And if we use Tauchen's method, which is described in the book, which approximate this RA process by a Markov chain transition matrix here, we derive the probability matrix here, the transition matrix 27. And as you can see, there's a high tendency of the households to remain in the same productivity class, which is described here by the diagonal. So it's around 0.7 on average. So with a probability of 70%, we remain in the same productivity class. And for example, the lowest productivity, they advance in the next productivity class with a probability of 22% to the third highest productivity with only a probability of 0.6%, and they cannot get to the highest two productivities. That's how we interpret this, this calibration matrix. Okay, so this describes our model and our calibration, and you find the details, especially with regard to the equilibrium conditions of the stationary variables and with regard to this calibration of the Markov chain transition matrix in the book. Let us pause here for a second and reconsider what we've done so far. So we have set up a model which, according to me at least, is the prototype model of income and wealth distribution to study redistributive policy in general equilibrium. We have replicated the age structure. We started with the inequality in the wage distribution. So we have replicated the cross-section Gini coefficient of the wage distribution. We have replicated the wage structure, the heterogeneity between generations, between cohorts, and we have also replicated the distribution, the inequality within a cohort. So all the aspects of heterogeneity, of wage heterogeneity, is captured by our model. And we have, with endogenous labor supply, we have also derived endogenous earnings. And we will find out that starting from a Gini coefficient of 0.375, we were able to replicate the cross-section earnings and income Gini, which are around 0.5. Because people with higher productivity also choose to work longer hours, and wealthier people reduce their labor supply. Poorer people supply higher labor, supply more labor. And this results in more heterogeneity in earnings and income than in the wage distribution. And with endogenous savings, we can even show, like Haggard did in 1996, that this generates even more heterogeneity, more inequality in wealth holdings. So we get a Gini of 0.66, and this is a very long way already to the inequality in the wage, in the wealth distribution, which is even higher in the United States. It's around 0.8. Now to get to 0.8, you probably need something like entrepreneurship. Entrepreneurs, they make up a lot of the top percentile in the wealth distribution is made up by entrepreneurs. And this is kind of tricky to model. Well, you need, in this case, let me just give you a hint how this is done. You need two kinds of households, the workers and the entrepreneurs. And the entrepreneurs, they have a different skill, entrepreneurial skill, to build up a business, for example. And you also have to somehow model these entrepreneurial skills and have to estimate them empirically. And this is much more difficult than estimating the idiosyncratic productivity of workers. Why? Because We have many more observations of workers than we have on entrepreneurs. So if you look at the data set of the consumer survey dynamics or the PSID, the share of entrepreneurs in the population, in the economy, in the data set is small. So therefore we can get only little data, very few data points, and this makes it difficult to estimate this process. And it doesn't stop there, because next what you have to endogenize in these models is, of course, entrepreneurs. Well, they hire people. Some just run the business by themselves, but many also employ other people, and they need a credit from the financial sector to invest in their business and build up their business. So we need to introduce a credit sector and somehow have to decide how a loan is extended to the entrepreneurial sectors. And as a consequence, this model is getting much more complicated, and I would like to encourage you to look in the work by Quadrini in the year 2000, but also a more recent work by, for example, Cargetti and Denardi, who modeled this sector, and it basically takes the same computational time on top of what we will need to compute our household sector to also endogenize, integrate an entrepreneurial sector into our model and get the top percentiles of our wealth distribution. All right, and now I will tell you how we compute this endogenous distribution of wealth and earnings in our model, how we compute aggregate savings, how we compute the policy functions of our individuals, our value functions. So let us go back into the slides. And let me just read to you the algorithm here. So first we parameterize the model and choose asset grids for the individual state space. Step 1. The parameterization of the model is mostly done. We know this from the calibration section. Then we make initial guesses of the capital stock somewhere in the labor supply, mean working hours, labor income taxes, social security contribution rate, and government transfers. Somewhere we have to start with the computation of the policy functions and distribution. We also compute in step 3 the values of the factor prices, W, wage W, and the interest rate R, and the pensions in this model, which are given by the replacement rate, which describes pensions relative to gross wages. And we compute, that's the main step, step 4, the policy function of the individuals using value function iteration. So therefore we start at the age 70 in the last period of their life, where it's really easy to compute the behavior, the policy function of the retirees, because they basically spend all they got and consume it. And then we work backwards in life until period 1, the first period of their life corresponding to age 21 in real life. Given our policy function, we start to compute the distribution, and there we iterate forward. So we're starting in the first period of life, because we know there everyone has 0 wealth, and then we just iterate forward to compute the whole distribution. And when we get the distribution, we can compute aggregate savings, aggregate labor supply, mean working hours, aggregate taxes and transfers, aggregate bequests as well from this distribution, update our aggregate variables, and return to step 3 and do it all over again until our capital stock and our labor converges. And then we check if our policy functions and our distributions are well chosen, our grids over the state space. So do all the chosen wealth levels lie inside our interval that we have chosen for the individual state space. And these programs are available to you as a download. The program is called AK70 Stochastic Income. It's available in Python, Julia, and Gauss. You can download it, and I already pointed out the download page. And the Python code is explained line by line, so I will not get into the coding in this tutorial here. But hopefully some of you will check my my tutorial on the web. So let's go through the single steps here, through the 8 steps. Step 1, we parameterize the model and choose asset grids for the individual state space. So we start with 500 grid points of the policy function grid, and we choose 1000 grid points for the distribution function along the dimension of the wealth grid, which we call A. Now, where do we get this number from? Well, this is a little bit experience, so I've done these models over and over again. 500 is a fair value to start with. We choose more points for the distribution function, and the reason is, well, later on we look at an accuracy measure. And accuracy of our policy functions, of course, depends whether we look at it on the grid point of the policy function, where it's very likely that we have a good fit. And if we are off the grid points and we need to interpolate some kind of behavior, well, it's more likely that at these in-between points, well, our approximation is less accurate. And that's why we choose more points along the distribution grid than for the grid of the policy function. We choose equispaced points, so in fact we will choose intervals from 0 to 20, so 0 is the lower bound on the asset, we have this credit constraint, and we choose 20 at the upper point. And we, of course, once we are done with all the computations, we have to check whether this is a good choice, whether there are some individuals who hold, or a lot of individuals who hold 20, an asset equal to 20, or if there are only people who hold a maximum wealth of, let's say, 1 or 2. Then we have to adjust the grid, so that the highest wealth level, they're basically 0 who hold it, but just a little below we find households who hold wealth level close to the upper boundary. So then we have chosen an ideal grid. We compute the stationary cohort shares μs of the S-year-old. And to do this, we just we start the iteration setting the measure of the 1-year-old equal to 1 and iterate over the next ages s equal 2 up to 70 by using this iteration 28. So we take, for example, the 1-year-old, which will have measure 1. They survive, let's say 90% of them survive, so that we have measure 0.9 in the next period. And because population grows, let's say again by 10% to make it easy, by 10% means that their size shrinks relative to the total population size, and we have to divide it by 1 plus n. So in this case, we would have measure 1 times 0.9 divided by 1.1, something like 0.8 would be the measure of the 2-year-old. And we continue to do this until we have computed the measure μs for all ages s, and then we just divide each measure by the sum of these measures to normalize it to 1, so that the total number of people, the total measure of people in our economy is equal to 1. And our measures look like this. So the largest number of people we observe at age 21, which corresponds to s equal to 1 in our model, and then it declines monotonically, and then the decline is larger due to lower survival probability in old age. Okay, and that's the distribution of a young economy. We have lots of people at age 20 and 30. That's different in the United States than, for example, in Germany, or in Japan, because the Americans have a high population growth rate. So, for example, in Japan, well, comparing the year 2000 or with the year 2050, well, Japan population will shrink approximately by 1/3, from 120 million to 80 million. So in Japan, this curve looks different because we have such a low fertility and such high survival probabilities. In this second step, we make an initial guess of the steady state values. Well, is not crucial for the convergence of our algorithm. So with this algorithm, it's really robust. It will converge almost independent of what we choose initially. But if we have a good initial guess for our aggregate values, then the convergence, the iteration over the aggregate variables, the outer iteration, will be faster. And we, of course, we want to save on computational time. So we choose an average labor supply of 30%, 0.3. And then we guess that efficient labor is also 0.3. So efficient labor is working hours times individual productivity. Now, we have to take account for the fact that only 78% of the population are workers. The remaining 22% in our economy are retirees. So we would have to multiply 0.78 times the average working hour, 0.3, times the effective labor. And as the more productive people work longer and harder, well, this pushes there's at least we can suppose that aggregate labor supply uppercase L is close to 0.3 as well, because what we have in shortfall here, because of the workforce share, we might make up by the longer working hours of the high productive people. Now we have aggregate labor, we set an real interest rate of 3%, and this implies a capital stock of 1.708 from the first order condition of the firm, that R is equal to the marginal product of capital. Now capital is not the only asset in our economy. So we know that the debt output ratio is 63% in the United States some 10, 20 years ago. This is no longer the case, but let's take this value here, 63%. Now, if our capital output ratio is about 3, that's what we observe in the United States, approximately 3.0, well, we can compute the shares of government bonds and capital in relative to total output, and then we have the shares of bonds and capital in total wealth, and from this we can compute that our total savings, total wealth, omega is approximately 1.26 of capital. These 2.6 times capital, that's what we hold in the form of government debt, and it follows by just using these two conditions here, plus the condition that omega is equal to k plus b. We set our transfers to a small constant because we really have hardly any prior on this, so 0.01. I set it to a positive constant, so this makes our algorithm much more robust if we don't have, for example, any negative values of consumption to take care of when our labor supply or labor income is small. Okay, now we have some initial values for K, L, and transfers, and this helps us to compute the wage and the marginal product of capital, W and R, and the pension is computed with the help of the replacement ratio. So pensions are equal to the replacement rate times the wage, W, times average labor supply. That's how the pension replacement rate is defined. So these 3 steps are fairly easy. Now comes the difficult step. We compute the household policy function with value function iteration. So here I've rewritten the Bellman equation so that the value of an individual characterized by the state vector zz is equal to the maximum of utility today plus discounted utility, expected welfare tomorrow, with a discount factor beta times phi s, and we know the transition probability from idiosyncratic productivity theta to theta prime, and we also have to multiply the value function next period by 1 plus GA to the power gamma times 1 minus eta, because our consumption, everything is growing, and therefore to consider stationary variables, we simply divide the value function by aggregate productivity 8t to the power gamma times 1 minus eta. We could have named this value function here v tilde, and I was a little sloppy here in this regard, but to keep the notation simple. Now, how do we compute this? Well, we will use Gauss section search, and let me show you this on the whiteboard. Okay, I hope you can read this. Here's the Bellman equation. I dropped the term with the utility from government consumption because it does not affect our optimal policy function. It only affects the level of the value function here. So do not worry about this one. And the household maximizes utility next period plus discounted value next period. Utility this period, discounted value next period. And what the household is doing is to maximize this right-hand side of the Bellman equation with respect to a tilde prime here. And if we do it, consider it for the worker, we also have label M. Now let's just look at the one-dimensional problem where we solve this thing for the next period values A prime. And I will explain how we solve it with respect to L in the next step. So the right-hand side of this equation, the right-hand side of the Bellman equation, is a concave function of individual next period values A prime. We use Gauss section search to find this value. So what you need to do with Gauss sections search, you need to specify an interval, let's say A0 prime and A1 prime, which contain the maximum. So one way to do this is to start with the low values level and then go up. And once the value of the right-hand side starts to decline again, you stop, because then you have the upper point for your Gauss section search. And that's how we're going to do it. And we also have to provide an intermediate point, let's say point A2, which is on the middle point here. Okay, what's the idea of the Gauss section search? Well, you have these 3 points, and then you choose, well, let's look at the larger interval here. You choose a point in between. And, well, let's take one that's easier to interpret. And this point is above this point. So then you know that the maximum must be in this part of the curve. So it must be between A2 and A1. Now the next step, we choose these 2 points as our boundaries, and again choose a point in between here, and consider these 2 inner points again, and see that this point here is above this point. So what we do is, this becomes our next interval. And as you can see, this one shrinks, and you will find the maximum relatively fast. It's called Gauss section search because the way you pick the next point, you use a special distance from the old point, and that's the Gauss section. And it's a very robust optimization routine. That's why I often choose it. It's relatively fast, and we stop once the 2 points are, the distance is below 10 to the power minus 5, then we stop this algorithm. So that's Gauss section search, and it's explained in more detail in our book, of course. Now, when we also do this optimization for the worker, we also have to optimize with respect to the labor supply. For the retiree, it's just 0. The retiree does not work. And what we do is we have two optimization problems now, a two-dimensional optimization with respect to A prime and with respect to labor L. Now we apply a nested research. So the outer function that we would like to maximize, it's a function of the next period Wells level A prime. And for each Wells level A prime, we use the first order condition of the household with respect to labor to compute labor supply. So this is done here in equation 31. So this equation here is the first order condition of the household with respect to labor. So you can compute labor here from this equation. All these parameters are given, and the present period level wealth is given, and if we optimize over A prime, then also A prime is given. So this is a nested optimization procedure. In the outer loop, it's A prime using Gauss section search. In the inner loop, in the inner function, it's labor supply L. Now we also have to make sure that the labor supply is positive, and it's between 0 and 1. And of course, we check this. So if this function here only describes labor supply, if labor supply is larger than 0, and if the right-hand side of 31 happens to be negative, we set the labor supply equal to 0. So we formally impose a non-negativity constraint on labor supply, which makes, of course, perfect sense. Now we solve the value function starting in the very last period. In the very last period, given that we have Wells level AT, where uppercase T is the maximum number of years in your lifetime, so we set T to 70. We know that we get our income, our pensions, our wealth plus the interest rate and transfers, and we spend it completely on consumption and have to pay taxes tau c, as given by equation 33. And we can just plug it into our utility function and compute the value of the value function with the help of the utility function for this consumption value c. And we can do this for all our grid points A that we have specified in our algorithm. Notice that it's independent of the productivity level. So for the retiree, it doesn't really matter whether he has productivity level theta or and E in old age. Just his accumulated savings are determining his felicity, his utility. So we only have to save the value function for the retiree for all the grid points A. And then we go backwards in time and look at the optimization problem of the 69-year-old. And the 69-year-old optimization problem is described by this Bellman equation. So our Bellman equation for the 69-year-old given as a function of his wealth level at 69 is, of course, again his utility from consumption at age 69 plus discounted value at age 70. We have all the values at age 70. We have computed it in the first step. And now we just solve this Gauss section search problem that I have described to you with this optimization problem. Now, of course, here this optimal policy in the wells at age 70 in the next period for the 60-year-old may not be a grid point. We only have 500 grid points, so it may be between 2 grid points. And what we will do then to compute the value at age 70 of grid points, well, we use interpolation. And you can specify 2 different kinds of interpolation schemes in the Python, Julia, or Gauss languages, programs that I provide to you, either linear or cubic. And we continue to iterate the value function for the retiree until we get to age 46, the first year of retirement. Now for the worker, we need to compute many more grid points because we have now 5 individual idiosyncratic productivities, theta 1, theta 2, theta 3, 4, 5. And we have 2 permanent productivities, E1 and E2. And for all these productivity types, we have to compute the value function and the optimal policy at the 500 grid points. So we again maximize the right-hand side of the Bellman equation, and each time we search over the optimal next period values A prime, we also solve the first order condition with respect to labor so that we can compute consumption and so on with the help of our solution for the optimal labor supply and for given next period values. Okay, that's a really time-consuming step, because let's take a look how many grid points we need to evaluate. Well, the number of grid points is the 500. It's NA plus times NE plus N theta times tau W plus NA times TR. So the number of grid points we compute the policy function is, in fact, is 237,500. That's the number of grid points we need to compute the optimal policy function for. So this is, of course, very time consuming. We need to solve more than 200,000 optimization problems in one outer loop over the aggregate capital stock. And as we will see, we need some 25-30 loops over the outer aggregate capital stock. So this means we end up computing more than 6 million optimization problems. And these are not simple optimization problems. They're a little bit involved. So as you can imagine, this might take some time. Okay, and here is, let me show you the optimal policy function of the labor supply of the low-skilled and the high-skilled, the college and the high school graduates. And as you can see, labor supply is a negative function of wealth. So the wealthy do not work less, and for the low-skilled people here, they work less than the high-skilled people for every level of wealth, just like we observe in the United States. And the non-negativity constraint on labor supply, so that labor is equal larger than 0, starts to bind for the low-skilled here at wealth level 12.5. So this is the particular labor supply of the 21-year-old, if I can remember, with productivity theta 4. Now, given these policy functions, we somehow need to determine, well, what's the accuracy of this solution, of our policy function. And you already know this from previous chapters, from chapter 7 and 8, and from chapter 2 or 3, where we looked at the so-called Euler equation residual. And it goes like this. We start from the first order condition of the household, its Euler equation, with respect to optimal savings. This is the second equation here, so that the marginal utility from consumption today is equal to the expected value of next period marginal utility times beta times 1 plus RB times phi s times this factor here that corrects for productivity growth. So that's our first order condition, or our Euler condition, or Keynes-Ramsey rule, as you may also know it, for the household with respect to next period wealth A prime. Now, if you reformulate this equation, we get to this equation here. So if we reformulate it in an implicit fashion, we get to this equation here, and equation 35 is equal to 0 if our equation is fulfilled exactly. So if we plug in our optimal policy function for consumption and labor supply and compute it at different points, well, it's going to be, if this equation here is equal to 0, then we know, okay, the Euler equation residual is 0. And of course, we would like to minimize the absolute value of these Euler equation residuals. So we compute it on many points. In fact, that's another reason why we use more grid points on the distribution than on the policy function, and compute and see whether our Euler absolute Euler equation residual is close to 0. Okay, let me give you the results here for our Euler equation residual. So if you, for example, use linear interpolation of the value function next period, our Euler equation residuals are 0.00085, so 0.085% for the young and 0.231% for the old, if we use linear interpolation and 500 grid points of the policy function. So, given that our golden section search has an accuracy equal to 10 to the power minus 5, we see that our Euler equation residual is not so far off this accuracy of our golden section search of our optimization routine, and we can be quite happy, quite confident that we are doing fairly well. Step 5, computation of the distribution function in stationary equilibrium. In this step, we compute the distribution of the assets of individual wealth at all ages S, all permanent productivities E, and all idiosyncratic stochastic productivities theta. We discretize the asset grid, the wealth grid, A min, A max with 1000 points, and we had chosen A min and A max equal to 0 and 20 respectively. Now, how many measures do we need to compute for our discretized distribution function? Huh? We have to approximate this infinitesimal object here, the distribution function, in the continuous state variable, by, of course, a discrete frequency distribution here, because the computer can only handle, of course, finite objects. And we have chosen that we just compute it at 1000 grid points in each of the wealth, 2 grid points here for the permanent productivity, high school and college graduates, 5 idiosyncratic productivities, theta, and for the 45 years of a worker. In old age, the policy function does no longer depend on productivity, because only labor income depends on productivity, but pensions are unrelated to productivity. So we computed for 1000 points times the 25 years during retirement. And this gives us a total number of 475,000 grid points where we have to compute the distribution function. Remember that the policy function was only computed for a grid over individual wealth of 500 points, so we just have to divide this number by 2 to get the number of policy functions that we had to compute in the value function iteration in step 4. Now in the programs, this is stored in an array. We called it GKW or GKR for the worker and the retired person respectively. And you may look it up in the program AK70 stochastic income.py for the Python program, GL for the Julia program, or GSS for the Gauss program. And you can all download it from our homepage and find the Python tutorial, the Jupyter script in the web, and I've given you the web address. Now we started the value function iteration in the last period of life at age 70 and worked backwards until age 1. And now to compute the distribution, we iterate forward. We do forward induction. We start at age 1 because we know this distribution and then work up our way to age 70. So what we do know about the distribution at age 1 is all households are born with 0 capital. So that's only for the grid point a tilde equal to 0 that we have a non-zero measure there. We know that the measure of the households at age 1 is equal to mu1 their share. So if you remember what we computed a minute ago, we computed the measure of the 1-year-old corresponding to the 21-year-old in the data equal to 0.02 something in stationary equilibrium. That's our measure mu1. And we know that half of them have high permanent productivity, are college students, half of them are high school graduates. So that's where the factor 1/2 comes in. And we have the measure V of theta of the different productivity classes that we derive from the calibration. So if you remember, we derived about an hour ago, we derived these measures of the idiosyncratic productivities. So for example, let's take a simple example. Theta 4 has measured 0.2101. So 20.1% of the workers have productivity theta 4, and theta 4 is equal to 1.4605 according to our calibration. So we can compute the distribution at age 1 for productivity theta and permanent productivity E at wealth level 0 is equal to 1/2 times mu1, which is approximately equal to 0.02 times mu of theta, which is equal to 0.2 for the case of theta 4. So for theta 4, we get approximately a measure equal to 0.00213. Okay, and we can do this for all the other grid points at age 1. All other grid points where A is larger than 0 are equal to 0. And the other grid points, we simply have to compute the share of the theta of the agents with productivity theta to compute the measure at these grid points. Okay, that's how we started. Now we have the distribution at age 1. Next, we want to compute the distribution at age 2. So what we do is we iterate over all grid points. Well, in this case, we only need, of course, the first grid point where A is equal to 0, but in later iterations at higher ages, of course, we need to iterate over all grid points and over all productivities E, J, and theta I theta. So over all permanent and stochastic productivities, and compute how many of those people at, let's say, a particular measure. Let's look, for example, at the guys who have wealth 0, the low permanent productivity, the high school graduates, stochastic productivity 1.4604, the second highest idiosyncratic productivity, and at age 1 they have measured 0.0213, and we wonder what will be the measure of the households in the next period. So these households, they have an optimal policy, which is also saved in a function. We called it AWOPT for optimal next period assets A of the worker, and we stored the value 0.08365. That's next period worth of this agent. And we know how many people will end up at this wealth level. Well, we start with 0.0092129 at this particular grid point at H1. Of those agents, phi1 will survive. That's the survival probability, which survival is stochastic. And we have to consider that next period, total population has grown by 1 plus n. So the measure of these people, if the measure is normalized to 1, the share of these people in total population has shrunk by the factor 1 over 1 plus n. There are fewer people now in the total sample. And this division by 1 plus n corrects for this fact. So that next period at hs plus 1, 0.00211111 is the measure of the agents who started with 0 capital and permanent productivity E1 and idiosyncratic productivity theta 4 at H1. Okay, now then the next point we notice is that A prime 0.008365 need not be a grid point. So of course, even the probability that it's a grid point is close to 0. And it falls, in this case, between the first and the second grid point, between 0 and 0.0202. So let me show you this on the whiteboard. So A tilde at HS1 is equal to 0, and H2, in our particular case for this particular productivity type, it's equal to 0.08. And the grid points which we using for A prime are 0, 0.02, 0.04, and so on. So what we observe is that the next period, as that falls between these two grid points, let's say at this point here, 0.08, and as you can see, approximately the two distances to the next grid points are related approximately by the factor 0.4 and 0.6, which I will use as an example. Now, how do we allocate this optimal next period to these two neighboring grid points? We don't have a grid point at 0.08, so somehow we have to allocate this new measure either to this grid point or to this. Well, it makes, of course, perfect sense that we take, and let's call this measure here, our measure was f of 0, theta 1 was equal to 0.57, theta 4 was equal to 1.4 at H1. The measure of this was approximately 0.002 or something like this. So we allocate this measure with the shares 60% to this grid point and 40% to this grid point. Why? Because then the average value, the mean of the two measures that we allocate here and here, is again 0.08. So we have still the same mean when we aggregate all the capital stocks, all the wealths at H2 and add it to our aggregate wealth. So when we add up all these numbers in step 5, so we keep the same mean, 0.08. And so is this approximation perfect? No, of course it's not. So let's assume this is our A tilde in period S equal to 2. And this is A tilde prime, which is the wealth level in period 3. So this is only a perfect approximation if we have a linear function, a linear savings function. In this case, of course, then it doesn't matter if this interval is short or large when we go to the next age, to the next period, when the age becomes 3, because then the average of these two values here, of the two next period values, will again be equal to the exact value of A prime in period 2. So we can, this approximation is only exact if our policy function with respect to wealth is linear. So this is described here by how we allocate the measures to the different points A1 and A2. This is described here. So we can also think of it as a lottery. So with a probability of 60%, people get allocated to point A1, and with a probability of 40%, they get allocated to point A2. And additionally, we have to consider that the idiosyncratic productivity changes. So we start in period 1 with the productivity guy theta 4 equal to 1.4, and of course his idiosyncratic productivity at age 2 in the next period is stochastic. We have to consider that, well, there's a certain probability that he might end up with theta 3, theta 4, theta 5, and so on. So we know this from the calibration. Remember that we estimated the Markov chain transition matrix using Tauchen's process. So if we start with the person at productivity 4, which enters in the 4th row of this matrix, well, he will have productivity 1 next period with a probability of 0, productivity theta 2 with probability 0.46%, probability theta 3, that's the example that we look at right next, of 20.1%, and so on. So we find that we have to allocate the measure at point A1 equal to 0 at permanent productivity E. He doesn't change his permanent productivity, and the productivity theta 3 at H2 is equal, that comes from this household at H1 with 0 productivity and idiosyncratic productivity type theta 4 by 0.66 times the probability that we transit from theta 4 to theta 3, which is equal to 0.211, times the measure of this household at H1 with idiosyncratic productivity 4, permanent productivity E1, and wealth 0, which is equal to 0.00211, times the survival probability over 1 plus the population growth rate n. And this gives us the measure 0.0002525 that we add to this grid point A tilde E1 theta 3 2. And we continue to do this for all theta 1. So what we effectively do is we have an outer loop over S, H, HS. The next loop is over permanent productivity E. The third loop is about idiosyncratic productivity theta. The fourth loop is about the different wealth level A. And the fifth loop is about theta prime, the next period wealth. So we have 5 nested loops, and this is what really slows down our computation in Python. So let me show you the computational times for our algorithm here. In Python, it takes 33 minutes, while Julia and Gauss, they just take 8 and 11 seconds respectively. So try to avoid programming loops in Python. They're really, really slow. But with value function iteration and large-scale overlapping generation models with stochastic behavior, we have no other option than to program a 4, 5, or 6 or 7-dimensional loop, depending on how complicated you set up your model. And as you can see, well, it becomes prohibitive in Python, while it is no problem in Julia or Gauss to compute the stationary equilibrium. And that's why I hardly choose Python, but rely on Julia or Gauss to compute these large-scale models. But of course, you may be more efficient in programming this than me and come up with a new algorithm where Python is really fast, but quite frankly, I doubt it. Okay, why is this a really valid and nice comparison? Well, we have used exactly the same number of operation and steps and computations in each of the program Python, Julia, or Gauss, and we have even stored the numbers with the same accuracy, so 16 digits. So as a consequence, everything, storage, operations, is exactly the same, and it's, I think, a fair comparison if we find out, well, Python in this case is a couple of 100 times slower than Julia or Gauss. And computational speed with large-scale overlapping generation models counts. Okay, you can speed up this kind of computation perhaps if you make use of multi-threading and parallel processing, which I have not done. So feel free to improve upon these times. But to have a fair comparison, I also did not speed up for the Julia and the Gauss codes as well. Now, once we have computed the distribution, it's quite easy to compute the new aggregate values. So we can, for example, compute the aggregate wells here by summing up all the measures times the wells level A, which will give us aggregate wealth. The same for with regard to aggregate labor supply. We just sum up all the optimal labor supplies, which we have stored here, times the individual productivity, which is the H component, times the permanent component, times the idiosyncratic stochastic component. YS times E times theta. We have values of K and L from the start of the iteration, which gives us output and hence our calibrated value of government debt, which is 63% of output. And with the help of all these numbers, with the help of B, government debt B, and aggregate new wells, omega, we can compute aggregate capital stock. So we have aggregate labor, aggregate capital stock. We can compute the new pension contribution rate tau P with the help of the social security budget. That's fairly easy. So we can just solve for tau P. And as a consequence, we also have the new value of the wage tax tau L, because the two tau L plus tau P sum up to 28%. That's how we calibrated the model. Government consumption is 18% of output. We can compute the accidental bequest. So we look at the optimal next period value of the optimal savings of the household multiplied by 1 plus R, 1 plus the interest rate, and by the dying probability times 1 minus phi s, and just add up all these bequests to get to total accidental bequest. And we can also compute aggregate consumption by summing up all the individual consumptions, C, times the respective measure. So optimal policy function, consumption, we have stored this as a function of H, permanent productivity, E, idiosyncratic productivity, theta, and wealth A, and we multiply it by the consumption policy function to get aggregate, sum it all up, and get aggregate consumption. So we can compute total taxes as labor, wage taxes, capital income taxes, consumption taxes, and then we can solve the government budget for the transfers. So we have to look at equation 9, the government budget. Government debt relative to total productivity and population. So the government debt per capita in stationary variables is constant, and if this variable tilde b is constant, well then this reduces here to 1 plus g times 1 plus n times tilde b minus 1 plus rb times tilde b. So we get to this equation here, to the bottom equation on slide 59, and we can solve for transfers as a residual from the fiscal budget. Well, and then we have computed all the variables that we need and update the aggregate values of the capital stock, labor, the two tax rate transfers, and average labor, which we use to compute pensions. And the different methods how we can update these aggregate values, we use a very simple updating scheme. So we take 80% of the old value plus 20% of the new value. Of course, this will determine the speed of convergence. 50% or 50% might be faster, but it might not converge. So, well, that's just rule of thumb value that I always use here, 80 and 20%. That's what I find is really robust. You may also try different updating schemes, and I have described them in the book. So you may also use a Newton-Raphson algorithm to update your aggregate variables here, these 5 variables, and check which one is faster. So I just use this fairly simple scheme, and in particular, if you write such a code for the first time, well, it's really helpful. You see that if the variables converge nicely, and it's really easy to program. So I often start with this simple updating scheme in my large-scale OLG models. And once you have done this and the outer loop over the capital stock and the other aggregate variables converges, you're not done. You still have to see if you have specified the grid reasonably. So is the upper limit A max, which we set to 20, binding? Well, we find that some households, the very rich households, the maximum wealth that we observe is something like 15, 16, 17. So this is a really reasonable choice. It's not, so we have no positive, strictly positive measure of agents and the upper limit A max equal to 20, but we get close to it. Otherwise, we could shrink the interval, the upper limit, and of course this makes our computations more accurate. And the second thing you should do is to check your Euler residuals. Is the accuracy satisfactory? So let me show you the results that I already presented to you in the beginning. We used in the benchmark linear interpolation 500 grid points over the asset space for the computation of the policy function, 1000 grid points for the computation of the distribution function. The accuracy as measured by the average absolute Euler residuals is equal to 0.085% for the young and 0.23% for the old. And that's close to the accuracy of our golden section search of our optimization scheme, 10 to the power minus 5. So we are, well, can be quite happy. In fact, I've computed models with much worse accuracy. Okay, now let's look at the runtimes. Which is our perfect program here? Well, in this case, Gauss is the fastest, 27 minutes. Julia is 1 hour 30, and Python is really slow, 32 hours. My God. Okay. Well, you're invited to speed up the Python program. I just programmed it in a similar way like the Julia and the Gauss program to make it comparable. Now, if I rather choose cubic interpolation, so the interpolation is of the next period value function in the Gauss section search algorithm. So I compute the right-hand side of the Bellman equation, utility today, instantaneous utility today, plus discounted value function next period, and the next period value function I have to interpolate because the optimal next period wealth may not be a grid point. And when I use a cubic interpolation, our accuracy improves by a factor, well, way above 10 here. Oh, no, approximately 5, sorry, approximately 5. So this indicates that our policy function savings or next period wealth is not a linear function of this period's wealth, otherwise these two would be identical. So first hint, okay, we have a non-linear policy function here from this exercise. Second, we find because cubic interpolation is so much more accurate, well, what is the trade-off in runtime? And as we can see, well, the runtime for Julia hardly increases. That's really a striking result. And this is must not be the case in other programs. So for example, in our Gauss routine or Python routine, our computational time almost doubles or even more than doubles when we go from linear to cubic interpolation. And therefore you have to check, well, which program do you use and how fast are my interpolation routines, linear or cubic? Does it make a big difference if I interpolate cubic? Well, in Julia it does not, at least in our interpolation scheme that we used. In Gauss and Python it did. And as you can see that the accuracy increased a lot. Well, let's look at the case that we use a smaller number of grid points over the policy functions, just 300 points. The accuracy then with the cubic interpolation method is still higher than in the case of the linear interpolation. So twice as high. The Euler equation residual is the absolute one is on average just half. By the way, we get the same numbers here for the Euler equation residuals for these three programs. They have exactly the same results up to 15 digits. So it's really an exact computation here with the three programs, exactly the same computation for the three programs here. So when we use cubic interpolation with 300 instead of 500 grid points, our cubic interpolation is still more accurate as in comparison with the linear interpolation, both for the young and the old retired agents. And for example, with Julia, it's much faster than the linear interpolation. So by going from linear to cubic interpolation in Julia code, we can increase both computational time, speed, and accuracy. So why not do it? So in Julia, I usually use cubic interpolation and a little smaller number of grid points, and it's beneficial, this trade-off. In other computer codes, for example, if we compare Gauss, Python, the linear and the cubic case, we still see an increase in computational time. So it really depends on the computer code that you're using, which interpolation scheme and number of grid points here is optimal for your purposes. And your purposes is, of course, some kind of different weights on speed and accuracy. So let me show you in the conclusion here the results. We find a hump-shaped age wealth profile. So the 21-year-olds start with 0 wealth. The maximum wealth at age 60 is around 3. So this is average wealth at age 60. Some will have 12, 15, individual wealth of 12, 15. The lucky, the high productive ones, and others have close to 0 wealth. And the maximum is attained prior to retirement at age 65. That's because our effective discount rate, beta times phi s times the survival probability, already starts to decline fast at age 60 and 70. Now our consumption age profiles is hump-shaped but displays a jump here, a discontinuity at age 65 prior to retirement and 66 during retirement. And that's because agents like to smooth under-temporal utility. And utility in old age as retiree increases because leisure jumps to 100%. At age 65 you will still work, let's say have only leisure of 70 or 80%, and in old age leisure goes up to 100%. And that's why you reduce consumption, so you smooth your instantaneous utility during the lifetime, over the life cycle. And our labor supply age profile displays the same kinks as our age productivity profile, but our age productivity profile peaks at age age 51, 52, and the labor supply, so the average working hours, they already peak at age 31, 32. That's because when agents get more wealthier and wealthier, with age they reduce their labor supply. So this is a wealth effect that our labor supply already attains its maximum at age 31, 32. The implications for the distribution of the earnings and wealth I've already pointed out to you. I pointed out to you in the beginning. We start from the wage distribution, which more or less exactly matches the US one, the empirical one. Earnings distribution here, the blue line is the US, the red line is our model, and we find that it's close. This is the data by, let me show you this reference here, by Boutier, Rodriguez, Diaz-Jimenez, Quadrini, and José Victor Rios-Roll. And if we take the data for the earnings quintile provided by Dirk Krüger, Mittman, and Perry in the Handbook of Macroeconomics in 2016, so they use different data, these two, PSID and CSF, well, then we get an earnings distribution which is closer to the one in our model, closer to the red one. So we are close with our earnings and also with our income distribution, which I do not show here. Our wealth distribution, well, we match the poorest 50% very closely, basically exactly, but we do not match here the top 1%, which showed about 30% of total wealth in the data and just 2 or 3% in our model. Now, how can we improve our modeling so that we get from a wealth Gini of 0.66 in our model to the wealth Gini in the United States of 0.80? Well, we need to integrate missing elements. So we do not model bequest. So we do not have bequest in our model yet. You can implement it in the standard model, and this is done by Denardi and Young. So we do not have, for example, the Rockefeller or the Hilton. So Paris Hilton is of course, she will inherit a lot of wealth and may not have a high wage. She has earnings, of course, high earnings, but compared to the wealth she will inherit wealth is perhaps little. So bequests explain a large part of wealth. We may introduce unemployment. So during times of unemployment, people run down their wealth, and this may increase inequality in wealth distribution. When we look at social security, we often find asset-based means tests, so that prevents people from building up higher debt, because if their wealth is above a certain threshold level, then they will not receive social security. But most importantly, at least in my view, is that we neglect to model entrepreneurship. We do not have the Bill Gates in our model. And two prominent papers who look at this, the first one who looked at this was Vincenzo Quadrini in 2000, and in a paper in the American Economic Review, Caggetti and Denardi looked at the entrepreneurship. And here, well, this is really tricky. Well, when you also want to model entrepreneurs, you need to distinguish two types: workers, entrepreneurs. And the entrepreneurs, they may have different productivities, they might have different number of people, they might invest in their business, giving the credit constraints and giving their own wealth, so and their own means. So this is a complicated modeling, and it certainly adds to the computational time, so, and to the complexity of the model. It basically goes up quadratically here. We have not modeled stochastic health, so Jung and Tran have this beautiful job in modeling this stochastic health in the Review of Economic Dynamics, estimate data, how health declines in old age, how it depreciates. So we treat it like a different asset. our health capital, and depreciates, and we can invest in health capital. So we add an additional state variable here, and this of course increases the dimension of continuous state variables by 1 and makes it a little bit more cumbersome to compute this stuff. But if you look at empirically, it makes a lot of difference if you consider stochastic counts or not. So the 70-year-old on average, as already pointed out, paper by Denali, they have something like $1,000 on average on health expenditures, and it goes up to $9,000-$10,000 just 10 or 15 years later. And this is really important for your motive, your precautionary savings motive. And last but not least, here there are many other aspects. Paper by Holter, Kruger, and Stepanchuk, if I remember correctly, yes, in 2019, Quantitative Economics. They show, they find, of course, empirically, we find that wealth is related to marital status. So married people are wealthy on average. And of course, if you get a divorce, it drains down your assets. You get poor very fast. One of the biggest risk is to get divorced. And this is, of course, also an important explanatory factor in the distribution of wealth. Okay, so let me summarize here. First of all, congratulations, you made it. You got through this almost 2-hour video, and it shows that you have some resilience and what it takes to become a good researcher. Now, let me summarize very, very briefly what we did and comment on it. So first we have set up a model of income and wealth distribution. Which I consider the prototype model for doing distributional policy analysis. We are able to match the cross-section and the cohort section and generational distributions of income, earnings, and wealth a little less closely, but also to some extent accurately. And if you consider something like, for example, fiscal policies or recessions, the COVID crisis, the Great Recession in 2007-8, on the wealth and income distribution, you use such a model. This model here, for example, may shed light on many issues. So, for example, we used a debt GDP ratio of 63% prevailing at the beginning of the century, but now due to COVID, the debt level in the United States is around 100% or above GDP, and you can of course compute what happens to the distribution of income and wealth if debt grows higher and higher. Let's take 200, 300, 400% and study in this model what happens to the distribution of income and wealth, and what happens, for example, to the real interest rate R in this model. So perhaps it explains why the real interest rate, let's say on 10-year treasury bonds, has been negative for the last couple of years, and what this got to do with the debt level and with the aging process. You can analyze this in this model fairly easily, just change the debt level and the survival probabilities, which have gone up or will go up, and the population growth rate that will go down over the next 20, 30 years. At least that's the projection of the United Nations. And of course, we can be fairly accurate with regard to the population growth rate, because those who will start working at age 21 in, let's say, 20 years, they're already born today. So we know about the size of the labor force in 20 years, except for the migrants. But leaving this aside, we can predict it fairly closely. So we can see whether whether aging, demographic transition, and higher debt might explain that, for example, the distribution has become more unequal over the last couple of years. That might be a subject of study that you might undertake with this model here already. So I consider this the benchmark model, the prototype model to study distribution issues, either redistributional policies or effects of shocks or developments like aging. Second, we have looked at computation. I've presented to you one way to do this with the golden section search, and you also can apply this to higher dimensional problems. We find this in our book by Alfred Mausner and me, Dynamic General Equilibrium Modeling. We will look at a higher dimension to introduce accumulated earnings and study how an additional continuous individual state variable affects computational time accuracy and so on. And third, we have looked at the three computer programs, Python, Julia, and Gauss, compared them with respect to speed, and found in our case, well, most preferably probably Julia and Gauss over Python. Julia is free, Python is freeware, so you can download it everywhere. You find more code in Python than in Julia. Gauss is a little bit more expensive as MATLAB, approximately. So if you want to start and do not want to spend a lot of money, well, I tend to recommend Julia. So my most recent PhD candidates, I asked them to learn programming in Julia. But Python is really popular. So when I look around at academic graduate programs or even undergraduate programs, so quite recently I found an undergraduate program at the UC Irvine, I think it was, where they introduce a computational course based on Python for the sophomore, for the junior or senior bachelor students, and do some of these general equilibrium models, for example, the neoclassical growth modeling, using Python code. So Python has become really popular, and that's also an argument, depending on what you want to do with your research, whether you want to do really complicated stuff like these overlapping generations models, or do more, well, simple computation. Well, then Python might be better for you. If you want to do something more elaborate, then I would recommend Julia. Now, with regard to the computation, let me mention one further issue. So in the first part of our book, we do representative agent models, and we provide you with a program that's called Quorum. And other people who are familiar with MATLAB, they use something, for example, like Dynar. And what you do in this program to compute the solution for the neoclassical growth model, for the standard business cycle model, you just plug in your equations, and the rest is done by the computer, by the code, Quorum code, or the Dynar code. This is not possible for large-scale overlapping generation models. Each case is different. You have to implement it individually, do the programming, do the coding. So that's when you look at the number of graduate students and their PhD thesis, which is done on representative agent models and those on heterogeneous agent models, you find out, well, with heterogeneous agent, you're certainly in an elite, in a small group of people, because you have to implement and think about the algorithm and the computation and programming coding, about the language, which one you use, and how you specify your model in more detail, and of course more complicated. Well, whether you will be more successful with this kind of strategy, that's for you to find out. And let me thank you again for reading or having a look at our book, following this long video, and I hope you enjoyed computation of dynamic general equilibrium models, in particular with heterogeneous agents. If you have any questions, comments, would like to ask me a question on the codes, Python, Julia, Gauss, whatever, on the particular code, or have a faster code than I implemented, feel free to send me an email, and I will be happy to reply to you.